question is, what are the different stages of the model building process? So the different stages of model building process are the following. You start with defining a problem statement, then you collect your data and you consolidate your data and come up with the final data set, and then you start cleaning your data set because most of the times your data will not be clean enough. Then you select your variables, which are the variables to be used in the final model, and then you start with variable exploration. We call it exploratory data analysis, which is nothing but exploring your data and variables and come up with the best set of data and best set of variables, which will ensure that the model is good enough for use. Then you develop your model and then you validate your model. So once the model is developed, you ensure that the model is going to work in the new data. So you do the out of sample validation and the out of time validation. Then we do model implementation. So once the model is finalized from the model validation step, we implement the model on the web platform or on a desktop platform. In the process, we start from the very beginning itself, we would have started the model documentation. So we finalize the model documentation once the model is implemented. We monitor the model on a regular basis. There will be slight deviation in the modeling steps depending on the kind of industry you're working with or depending on the company. So there will be some company specific steps. There are certain steps which are omitted, like there will be literature review, wherein you will be discussing or you will be finalizing the technique to be used. So we call that literature review. That's also an additional step which is performed. There will be several other steps related to data checking and validation. The next question is, what are the different variable detection techniques that we know of? Well, the most popular one in the banking and financial industry, also in the retail industry, is using variables or finalizing variables using the information value criteria. So the information value criteria is used to find out the predictive power of variables. So the one which are having good predictive powers are preferred and that is used for the model. And we also use clustering. Clustering is used to find out whether two variables are very highly correlated or highly uncorrelated. So we ensure that we select the independent variables which are highly uncorrelated among themselves. So we select a couple of variables from the cluster. So you will have a cluster variable. So we just take the best one or two variables from the particular clusters, because in a particular cluster most of the variables will be very similar or very highly correlated. So we'll just pick one or two out of these clusters. Principal component is also similar technique which is very similar to clustering, except some fundamental or computational difference. Principal components are used to reduce variables. So we come up with composite variables which are used instead of the raw variables or the original variables. So principal components are very useful visualizing the data and also coming up with a very smaller set of variables. But these are not very useful when the purpose of your modeling is to find out the relationship between variables. Principal components greatly helps when it's all about prediction, but doesn't quite help, or it doesn't help much when the modeling objective is to find out the relationship or finding out the marginal impact on your dependent variable. Then comes factor analysis. Factor analysis is related to a set of modeling technique known as the structural equation modeling, which finds out the relationship between different factors. So factor analysis is very similar to principal component analysis, except the fact that factor analysis is used only when you have causal hypothesis to be tested. Otherwise, it's not very useful. You can always go ahead with principal component. And factor analysis is also used for reduction of variables. You come up with a very smaller set of factors and come up with the finally build a model. Next question is, so what do you mean by exploratory data analysis? We talked about in the first question. So if somebody asks this, what exactly do you do in an exploratory data analysis? This is often a question asked because most of the times we concentrate a lot on the simpler techniques before going ahead to the more complicated and sophisticated techniques. So the exploratory data analysis, in short known as EDA, involves the following. We start with the basic descriptive statistics like mean, median, mode, minimum, maximum, number of missing values, and univariate analysis like your quantile plot, your quantile distribution, percentile distribution, and so on, extreme values, and so on. And then you visualize your data using graphs and plots, very useful to find out outliers, extreme values, and then find out a basic pattern in your data set. And then use more sophisticated univariate and multivariate techniques. So multivariate technique would be your correlation, principal component analysis, clustering. So these are the techniques used to find out relationship among the variables, which variables are highly correlated among themselves, which variables are very similar. So we can club them together and come up with a composite variable. So all these decisions are taken before even the model building is started. So that comes under the exploratory data analysis. More statistical plots like histograms, and then you use the quantile plot, the quantile plot for the checking of normality. Some models demands normality of your data, normality of your variables. The variable has to be distributed normally. So for normal distribution checking, you use quantile plot, and then the extreme value detection, which is also extremely important because a lot of time these extreme values create problem, and this has to be removed from the data set before even you can go ahead with the. The next question is, what are linear models, and how are they different from the non-linear models? A model is called linear when it is linear in parameter. Now understand this particular statement, the linear in parameter. So we cannot say a model to be non-linear if it is non-linear in variables. So it has to be non-linear in parameters. So a linear model is always linear in parameter, and I'll give an example which will be more clear. And the function which relates your dependent variables with your parameters has to be linear functions. So let's take an example. So y equal to a plus b x, where x is your independent variable, y is your dependent variable, a and b are your parameters. Now this is a linear model because both a and b are there in linear form. But if you have like a square or b square or square root of a, something like that, or logarithm of b, then the model is going to be a non-linear model. So an example of non-linear model is like this, where y is equal to a plus b square x. So this is a non-linear model. But remember that y equal to a plus b, y equal to a plus b x square is not a linear model. Y equal to a plus b x square is not a non-linear model. This is a linear model because it's linear in parameters. So a and b are parameters which are linear, so it's still linear model. So nonlinear model usually involves estimate terms like product of two parameters or square of one of the parameters. The next question is, what is the difference between a parametric model and a non-parametric model? Well, the main difference is the data which is used is assumed to follow some theoretical distribution in parametric models, like normal distribution, like binomial distribution, and so on. On the other hand, the non-parametric model do not assume any theoretical distribution. So what do you mean by theoretical distribution? Well, the theoretical distributions are the one that we might have studied in our textbooks, like your normal distributions, binomial distribution. So when you're doing a multiple regression, we generally assume that the error is normally distributed, whereas in logistic regression, there is an assumption of binomial distribution, right? So these two models, your multiple regression model and the logistic regression models, come under the parametric model. But there are models where there is no such assumption. So the algorithm itself finds out what exactly the actual distribution of the data from the data without assuming beforehand. So those models are known as the non-parametric model. So your example of parametric models are normal regression and the binomial regression, and the example of non-parametric models are the smoothing models, mostly the kernel smoothing model or a scatter plot smoothing model. So these models are the non-parametric models. The next question is, what is the main difference between a correlation and a regression? Well, the correlation is a two-way phenomenon. That means if x and y are two variables, so we try to see how x is related to y and y is related to x. So it's a two-way phenomenon. It talks about the strength of relationship between two variables from both sides, from x to y and from y to x. Whereas regression is always a one-way phenomenon. That means you always want to find out what's the impact of x on y. You don't do it the other way around, right? What's the impact of y on x? That's usually not something that we see, but there are models where we actually see the both way effects. But normally in most regressions, the impact or the relations will be one way all the time. The second difference is that a correlation doesn't give marginal impact. That means if we know that two variables are correlated and we know there is the correlation between these two variables, we cannot say if we increase one of these variables, say x, by 1 unit, what will be the corresponding impact on y. So that's not possible from the correlation. But in regression, you can always find out the marginal impact. That means in regression, for example, if this is the regression model, y equal to beta naught plus b1 beta 1 x, if we say that x increases by 1 unit, you can say what the corresponding increase in y is nothing but your delta y by delta x, right? So that's your marginal impact. Next question is, how is correlation different from causation? This is a philosophical question, little controversial, but one of the answer that you can give, which may not be 100% correct, because it's slightly confusing and also not a very clear-cut question, but a lot of people actually ask these questions, so I'm talking about it. So causal relationship is established when the relationship is very intuitive and it adheres to some accepted hypothesis. But correlation, which can be found between any two variables which are not at all correlated. So causation always has to be very intuitive or something that you can always expect. But sometimes the relationship between two variables could be spurious in nature. That means they are correlated, but in general, you won't find any relationship in the real world. So That's exactly is the difference between a correlation and causation. The next question is, how do you validate the input data sets used in the model building? This is often a question people struggle to answer, because in a lot of in a number of companies or number of projects I have seen, data validation is not a step. If you remember, in the first question, we did not talk about the data validation. We only talked about the model validation. But data validation is also an important step in the model building process. Many a times we get data from different departments, mostly the IT departments. Okay, and IT usually don't have very good knowledge of if the data quality is actually good enough for model building. Now, when we talk about data quality, there are different types of data quality which we need to ensure. So there are some IT specific data quality checks like format and so on. So these things are taken care of by the IT people. But there are some model specific data quality checks which normally ignored by the IT people. For example, one of the check is range check, right? You want your data to be falling under two particular limits. Say for example, one of your data set is a probability value, right? So probability always has to be between 0 and 1, right? It cannot be a negative number, and it always has to be between 0 and 1. Now well, the IT may not check this particular variable. So the modeling tips should ensure that another round of validation checks or data quality checks should be made before starting with any model development exercises. So that's important. So ensure that you double check your data source, whether the source itself is correct or is a reliable source. Otherwise it will be like garbage in and garbage out. So model results will be erroneous. Then apply common sense. So apply common sense sometimes. For example, the age of customers cannot be 200, right? So that's wrong data. So that you also ensure. And then compare data with previous year. The team which developed your model in the previous year must have done some validation checks. So always good to compare your data with the previous year data. But it doesn't mean that if it matches with the previous year data, it's good. There are it could have happened that in last year your team did not perform validation check properly, and there were mistakes. So that could be carried forward to the next year. So ensure that that is well validated with your previous teams. And then do some basic data exploration and visualization. A lot of this data issues or quality issues get caught when you actually visualize your data. So good to plot each and every variable so that you will find out some anomalies. The next question is, why is too many missing values in the input dataset a problem, and how do you treat missing values? This is an important question. In most technical interviews, you will face this question. Well, the missing values actually create problems for the algorithm to converge. A lot of time, if your data set is having too many missing values, it takes a lot of time to converge firstly, and also many a times your algorithm will not converge. That means if you're running a logistic regression or a discriminant analysis, most likely with a large number of missing data, it's not going to converge properly. There are techniques which takes care of missing values automatically, but these techniques are mostly used for prediction purpose. But econometrics models, mostly which are used for finding out relationship between variables, will have problems with missing data. So that should be corrected. So missing values are replaced by mean values of series and time series data. So replacing missing values in time series data is a lot more easier than other form of data like cross-section data. You know, in time series data, if like one of your variable is missing, you just take the previous values, because we we generally take the in univariate time series data. You'll always find the data for a particular event or a particular entity. So that data gets continued for a period of time, so you can use the previous period if that's for a particular period you don't have the data, or else you can also take the mean of the entire series and do the imputation. One of the industry very well known technique used in industry is the weight of evidence, or in short we call it as WI. So WI method of transforming your variables into WI variables ensures that your missing values are taken care of. So each continuous variables, even the categorical variables, can be converted into the weight of evidence variables. So weight of evidence variables generally make sure that your continuous data is grouped into categorical variables, and the missing data is considered as one category. Okay, so you can check the videos on weight of evidence. There is a playlist in my channel. You can see these videos, watch this video, and you will understand how weight of evidence can be used to treat missing values and outliers. The next question is, why is presence of outliers in the model a problem? Well, if you encounter a lot of outliers in your data, now what is an outlier in a data is actually difficult to answer firstly. So if you really think that there are a number of extreme values in your data set which are definitely different than most of other observations or most normal observations, then you call this these values as outliers. And not all the times though, because you have to be very careful. So this definition is slightly complicated and confusing. It's not that easy to find out outliers in your data set. Sometimes some data may look like extreme values, but removing this data will really impact the predictive ability of your model. So do a good check of whether your data actually has outliers and remove them. If you don't remove them, then you will find out that your standard error of the parameters will be a lot more than expected, and then your estimates are going to be unreliable. You cannot interpret your estimates. So that's the problem. So you should ensure that the outliers are removed. Thank you, and you can subscribe to this channel for more videos, and I will be uploading more question and answers sessions in my following videos.
One of the common questions people ask is, what are the steps involved in ARIMA model? Now, this is one in terms of questions which is a pretty general in the sense that most people use their own way of modeling ARIMA. But there's some standard approach used by people in the industry. It may not exactly be the same what people are using in different industry, but some of the common steps, there will be variations of it, but some of the common steps used in the ARIMA modeling are as follows. So you start with plotting your data. So you do your exploratory data analysis, pretty much like any other modeling exercise. What do you learn from the exploratory data analysis of the time series data is that you will you'll get an overview of whether your data is having seasonality, or it's showing some sort of a non-stationarity, there is changing variance, changing mean, and so on. So the preliminary idea is found by just plotting the data before even going to some diagnostic statistics. Okay. Well, if the variance is changing, sometimes it can be stabilized. Okay. There are some transformations which are available, like the Box-Cox transformations, which is useful to stabilize the variance, and that really helps making sure that the variance is uniform across the series. Sometimes even with a Box-Cox transformation, it's not possible to stabilize it. So you have to do a deep dive into the data to make sure that if it is if there is issues with your variance, or it's changing over time, can you stabilize it by Box-Cox transformation or some other transformation? Then you check for stationarity. Of your data. If it is stationary, that's good. You can go ahead with the next steps of modeling. But if it is non-stationary, either you can you can test it, the non-stationarity, or you can just do it by check it by plotting, or just use some statistical test to check for non-stationarity. If it is non-stationary, then you have to take the difference, right? So in one of the time series video on our channel, I have talked about how to do differencing and what exactly is differencing. So in the ARIMA model, the I stands for the differencing parameter. Okay. So when we talk about this P, D, and Q, so D is the number of differencing that you are doing in the ARIMA. Alright, then you check for the ACF, PACF, and find out the order of MA and the AR values. Okay, the MA terms and the AR terms. Okay, the order of MA and AR. And then once you're sure about how many number of differences are there, so you're sure about what the D term, it is 0, 1, or 2. Okay. If it is stationary, then of course it is going to be 0. If it is non-stationary, either it's going to 1, 2, or 3. So and then there will be certain AR and MA terms. So the next step would be to find out what is the optimal number of orders for AR, MA, and D. Okay, and that you can find out by using some some standard matrices. Okay, so what you can we'll talk more about it in one of the next questions. You can and that's based on the prediction accuracy and also some other means in which you can optimize it. But the idea here is that the D and Q value in ARIMA, right, should be in such a way that the model is giving high prediction or accurate prediction. It has high prediction ability or accurate it gives accurate predictions. All right, the next step is to check for the residuals. Okay, even if the model is able to provide good accuracy, how do we ensure that this is the optimum model? Okay, can it be made better? That you know by plotting the residuals. So the residuals should be white noise. That means the mean should be 0. The mean should be 0, and the standard deviation is 1. So that's standard deviation is constant standard deviation and constant mean, and 0 mean in particular, for it to be white noise and 0 autocorrelation. And why is it so? If it is not white noise, okay, if there is pattern in the residuals, there is pattern in the residuals and the residuals are correlated, then we are missing out on something. I mean, we are missing out on certain information in the model. So you need to go back and see if you can change the order of your ARIMA model and ensure that it can be made better. Okay, sometimes you may have to increase the number of differentiation. Okay, so you have tried for d equal to 1 and 2, so first difference, second difference, you might have to do higher differencing, like third difference and so on. Probably you might have to take let's say you have taken AR1, check for AR2, AR3 and so on. Similarly for MA, check for higher order of MA and see for which model the error or residual sums are following white noise. Alright, so when you put it in diagrammatical form, these are the steps. You start with some data, you plot it, take stationarity. If it is not stationary, then take the difference. If it is stationary, then check for ACF, and then after taking difference, if it is not stationary, come down to checking CF and PACF, and then find the value of the AR term, ARP, and the MAQ. Okay, so find out the value of P and Q in the terms, and it's not necessary that you always have to have a AR or P term. Sometimes P and Q can take any value, any positive value. They both could be 0 as well. Okay, and then you check for model fitness. You already have the value of D, the number of differences, and then once you have the value of P, Q and D, check for model fitnesses. That you can do by checking the archaic information criteria, and the one which is having the least AIC value or the most parsimonious value is the one which is fitting your data very well. And then another diagnostic check that is a compulsory test in ARIMA modeling is the residual test. Once you have fine with the residual, that means residual should be white noise. If this is not white noise, then go back. You have to go back and then do a better fit of the model. If it fits or it passed through the diagnostic checks for white noise, then you are ready that the model is good, and then you can do your forecasting. These are the steps. The next question is, what are the ways to determine the order of ARIMA terms? Okay, the previous questions we talked a bit about it, but we didn't talk about it in detail. Okay, if you go through my video on the time series analysis theory or the theory about ARIMA model, both these videos are there in my channel. You can go through them. I have explained in detailed manner. I'll just do a brief recap of what I've explained there, and I'll just explain what are the ways in which you can determine the value of P, D and Q. That means P is the number of AR terms required, Q is the number of MA terms, and the D is the differentiation. Okay, so we learned in the previous questions that the number of differentiation is entirely depends on how many times it has to be differentiated to make it stationary, how many difference it requires in order for the series to become stationary. Okay, so what it is a non-stationary term. When you take the difference of it, okay, let's say you are taking y minus yt, then if you plot it, it becomes more stationary. You may have to do another or maybe second differentiation, and then it becomes more stationary. Okay, and that determines what should be the exact value of D, or the number of differences that one has to take. So the value of D is fine. Now the value of P and Q you can get from the ACF and PACF, right? If you're not aware of what this ACF, PACF are, these are autocorrelation function and the partial autocorrelation function. So please go through my video on theory of time series analysis theory. You will it's explained properly. Okay, that you can do. Okay, however, these steps will not ensure that you have found out the correct order of ARIMA. Why so? Because you are taking a decision on P, the correct value of P, Q and D on a standalone basis. I mean, you are not combining them together, or you are not combining them together and finding out what is the optimal PQ and D. Okay. So that means P and Q are not determined based on how many differentiation or how many differencing is being done. Okay. And that's a problem. Okay. So jointly, finding out what is the correct order is important, and that can be found out only by looking at the model fitness. Okay. So let's say, to make it more simple, let's take an example. So you just found out a model which you think is ARIMA 111. Okay. So you found that there is only one difference required, and then one air term and one ME term. But and then maybe the error terms are also white noise. That means you can go ahead and finalize the ARIMA 111 to be your final model. But that's not the correct way of doing, because you can actually check whether how does ARIMA 212 behaves. Okay. Sometimes you will see that the prediction accuracy, or the accuracy of prediction for ARIMA 211 is better than ARIMA 111. Now, from the standard way of finding out the order of ARIMA, we have found out the first one, but the second one is giving the better prediction. Okay, since they are very similar, if the residuals are fine with ARIMA 211, so that's the better model. Okay, that's the second step in which twisting the order of ARIMA. The first few orders you will always find out in the preliminary steps, but you have to do a bit of twisting, or fine tuning of the orders in the next step. The third one is parsimonious. Okay, so you can check at the AIC and SBIC values. The one which is the least is also good. Okay, that means the lesser number of terms in the ARIMA model, the better is the model. That is expected. Okay, so if there is equal accuracy like ARIMA 111 and ARIMA 211, both are giving exact accuracy, then ARIMA 111 is preferred over ARIMA 211 because it's more parsimonious. Parsimonious is nothing but simpler. Okay, so it's just a jargon used for a simpler model, or model with lesser number of terms. Okay, the final question is, how do you validate the ARIMA model? Okay, you might have come across a number of videos on my channel where I have talked about model validations for multivariate models, like regression model, classification models. And the usual way of doing it is take, divide your data set into two types. Take, let's say, 60-70% of your data as training sample, okay, and then 30% of your data, 20, 30 or 40% of your data as holdout sample or testing sample, right? And then you build a model on training sample, test it on the testing sample. If there is consistency in the model results, then it's a it's a good model. Okay, you build a model on a training and then test it on the testing sample. So that's the usual way of doing for multivariate models. How does it matter in the how does it apply to time series forecasting? Remember one thing, for time series forecasting we take only one variable, right? It's a univariate time series, right? So the only way in which you can divide the sample, because you have to take the latest observation, so that you cannot put it in the holdout sample. Okay, so one has to be very careful while finding out the in sample and out sample, okay, or the training sample and the testing sample. Let's say you want to do prediction for stock market, and you have, let's say, data for the current period. That period has to be there in the training sample. So the in sample and out sample or the training and testing making sure that you have training data and then testing data will be slightly different for time series analysis. Okay. One thing people do, and I'm not sure to what extent that is theoretically correct, is that they take the full sample for the as the training data, and then they take smaller samples of it as the testing data from the training data, and then fit the model and check for the accuracy. Okay. That's also okay, and people use it, so that's one way of validating it, but that's not the it doesn't give I mean, one has to be a little more careful. That's exactly the point. The reason why I'm emphasizing a lot on this is because many times what happens is that since the only way you can you cannot choose random values from your time series data. For example, let me explain it properly. I think this is very important. Let's say we have data for last 10 periods, okay, from 1 2 to period 10. Okay, now you might wonder that, okay, maybe 6 periods I'll take in the training data and 4 periods I'll take in test data. That means, let's say you choose period 1 in the training, and then period 3 in the training, and then period 6 in the training. That you can't do. Remember, time series data has to be uniform. That means the interval between two data points in time series should be same throughout. Okay, that means you cannot take sample periods like that. Okay, and then that means you have to take the entire population in the training sample. Okay, however, for testing purpose, you can take a resample, take smaller sample out of this training, and test your model if it is working fine. Or maybe you can just test it for a historical time period which is similar to the current time period. Okay, the trend may not be same because in time series the pattern may not be same for two time period, but if they are same or similar to each other, you can test your model for the validation purpose, for just to check for the predicted values and the actual values. So that's one way of validating. And then the most important thing is the diagnosis of the residuals. Okay, the residuals in a good ARIMA model should be should be white noise. Okay, should be white noise. Okay, with all the properties like mean, zeros, and whatever. There are also some statistical tests you can do just to see whether it follows white noise. So if that is there, then theoretically the model is sound, and when the model is theoretically good, it is expected to, that's the best you can do about modeling. Of course, it might fail in future. Not all good theoretical models work well in the real-time scenario, but nothing can be done. I mean, theoretically, when it's good, you can be sure of one thing, that you can be it at least meets the baseline prediction. Okay, and it might fail in certain scenarios or in certain specific scenario. Otherwise, in the baseline scenario, will well be captured in the theoretically good model. Another important to remember is that the ARIMA model or most univariate time series models are preferred for short-term forecast. Okay, for forecast for next few months. If you're intending to do forecast for longer period, univariate time series models are not very preferred. So you better go for multivariate regression model for forecasting. With maybe you can include a time series component in those models that's also capture the time series aspects. But mostly times regression models are only for short-term forecast, and that's also need to be kept in mind. Okay, so thanks for watching, and please subscribe to our channel, and also please go to our website, which is in the description. Thank you. Thanks for all your support.
So one of the question that is often asked is, what is the basic difference between the three important terms? One is probability, the odd, and the odd ratio. Okay, odd ratio. Okay, so probability in logistic regression, in the context of logistic regression, is that the probability of an event happening, right? Probability of the event, right? Given different information about the event, right? So when we denote it as 1 and 0, we say that probability of 1, right? Probability of something happening. So it could be probability of default, or probability of churn. So default, churn are known as the event. So probability of that happening is the probability in the context of logistic regression. So what is odd then? Well, odd is the probability of event divided by the probability of non-event, or the event not happening. Non-event, that means the probability in the case of, say, default, the odd of default is nothing but probability of default divided by the probability of not default. Similarly, in the case of churn, the odd of churn is nothing but the probability of churn divided by the probability of not churn, or you can say retention, right? Retained. So that's odd ratio. So mathematically we define odd ratio as the probability divided by 1 minus probability. In the case of binary event, that means the dependent variable takes only two values, 1 and 0s, right? So probability of event and 1 minus probability of event, right? So that we call it as the odd. And the last one is the odd ratio. Well, odd ratio is just the transformation of odd. Okay, so this is odd, or odd ratio. Sorry, this is odd ratio. So the log odds. Sorry, the log odds. So what is log odds then? The log odds is nothing but the logarithm of odd. The logarithm of odd ratio is known as the log odds. And what is the importance of log odds in logistic regression? And why that logarithmic is being taken? Why can't a regression be done with 1 and 0? Why this transformation? Okay. Well, so the idea is to have a probability, find the probability, right? But probability lies always between 0 and 1, right? So the values are bounded. The values are bounded between 0 and 1. And in regression or any mathematical optimizations, it is good if the values are unbounded. That means the values lies between minus infinity to plus infinity, right? If the values of the dependent variable lies between two different different boundary points, then it's not a good for regression, right? Because the variability will be limited, right, within that range, which is not a good thing. Hence, if you take p by 1 minus p by 1 minus p, it is going to be it's always going to be unbounded, right? This is unbounded. Okay. And p by 1 minus p is always a positive number, right?
always positive. That means if you take 0.3 by 0.7, it's positive. 0.7 by 0.3, that's also positive. 0.1 by 0.9, that's also positive. That means this is always a positive number. Now when you take a logarithm of the log odds, this value can be between minus negative to plus negative. Why so? When you take logarithm of a fraction, it is going to be negative, right? So like in this case, if you take a logarithm of this is going to be positive. When you take logarithm of in this case it's going to be negative, and in this case it is going to be positive. When numerator is more, the logarithm of that value is going to be positive, whereas when the numerator is less, the logarithm of that is going to be negative. Hence log of odd is used so that the range of the dependent variable can be in between minus negative to plus minus infinity to plus infinity. So that's the intention. Another question that is often asked is what is the importance of the likelihood ratio test in logistic regression? Now this is important. Well, normally what people do is that once they have performed the logistic regression using any of the statistical software, directly they go into the results. Okay, so they look at the maximum likelihood maximum likelihood results, but that's not the proper way of understanding or understanding your results from the maximum from the statistical procedure. Why so? Well, before even you can go to look at the estimates, okay, you should see the likelihood ratio test first. Likelihood ratio test. So what is likelihood ratio? Let's first understand. So the likelihood ratio test says that at least one of the independent variable is impacting or affecting or contributing, you can say anything, contributing to the dependent variable, or finding out the probability, right? To the probability, finding out the probability value. That means, say let's say you're finding the probability of default, right, which is beta naught plus beta 1 x1 plus beta 2 x2, right? So there are two independent variable in this case. So the LR test or the likelihood ratio test will tell you that at least one of these two variable is impacting the the probability. Otherwise there is no point in going forward and looking at your results, final results from the maximum likelihood estimation or optimization. So the first thing is to look at that. So if the LR test says that none of this independent variable actually impact your dependent variable or contribute towards the finding of the probability, that there is no point in going ahead and look at and take a look at the MLE values, because the model itself is totally not explaining anything about the variation in the dependent variable. Hence, before even going to see the concordance values or the MLE estimates, one should look at the likelihood ratio test and ensure that the p-value is less than 0.05 in the case of likelihood ratio test. Ensure that this is true. If this is not true, then better you don't look at any other results in the logistic regression. So this has to be the basic criteria, or the first or the bare minimum criteria, before even you can go ahead with other results. Another question which is often asked is what is multinomial logistic regression and what is the ordered logistic regressions. Well, these are different version of logistic regression, which extends the binary logistic to multiple category of logistic regression, multiple categories of dependent variable. Okay, so you might have learned that in logistic regression we always have two values for the dependent variable, 1 and 0. Right, but many times we may need multiple categories. It need not be only two categories all the time. It need not be two category all the time. It could be multiple category. For example, um, so we want to predict who is going to come first, who is going to come second, and who is going to come third in a class. Okay, so there are three categories here, 1, 2 and 3. Right, first, second and third. Or we want to categorize the class into, say, different category: good students, average student, and bad students. So there are three categories, so we don't have just two categories in this case. So there we cannot use the simple logistic regression, which only uses two values for the dependent variable. So that kind of a situation is dealt by using a special type of logistic regression known as the multinomial logistic regression. So in the multinomial logistic regression, you cannot categorize or you cannot order the different values of the dependent variable. So one of the example could be the choice of color. Okay, so there are different colors. Let's say there is red, there is violet, green, and so on. And the objective is to predict which color is most favorite of a group of people. Okay, so what is the probability that red will be chosen by a set of people? So that kind of a problem is dealt by the multinomial logistic regression. The other one is the ordered logistic regression. In that, so it's different from multinomial logic in just one way. You can actually order these values. Okay, so one of the example could be ranking of students in a class. So ranking of, like, best students, average students, and then bad students academically. So that could be one ordered logistic regression case. And then a ranking of different teams in the sports event. Let's say there are 36 teams who are competing for 8 places. So top 8 places could be 1, 2, 3, 4, 5, and so on. So that is order logistic regression, where you can actually order in different types. You can order in ascending or you can order in descending fashion. Whereas in the multinomial logistic regression cases, you cannot order, for example, in the case of choice of color, you cannot order, right? You cannot say red is greater than violet, or, it's in between. You cannot order the choice of color. So that's multinomial logistic regression. So that's how they are different. Another question is often asked is how to take care of the nonlinear effect in logistic regression. So the nonlinear effect in logistic regression is taken care of pretty much the same way you do with the multiple regression. So what you do is that you do transformation of your independent variables, and that will take capture a lot of nonlinearity in your data. So you can take the logarithm, or you can take the exponential of your independent variables. You can take higher dimension variables of your independent variables, like if x is your independent variable, then you can take x square, you can take x cube, and so on. So that's one way of doing it. You just do a transformation of variables, take higher dimension, take nonlinear transformation, and then that's one way. The other way is to take the dummy variable. Let's say one of the variable is behaving like this, straight line, and then again changing. Now you can see that there is one pattern in this area and there is another pattern in this area. So why don't you take just divide it into two parts and take a dummy. Okay, take a dummy variable which which is 1 in this part and which is 0 in this part, or it can be 1 and 0 in opposite direction also. Okay, and then take an interaction of that. You can take an interaction of that with a number of other independent variables. So that's also another way of handling the nonlinear effect in your data. Okay, or simply you just put the dummy variable in the equation, and that also will capture a bit of nonlinearity, if not very efficiently, but yeah, it's certainly going to captures some amount of it. Okay, but ensure that by doing so, by taking transformation and adding more variables, or by taking dummy variables, ensure that the model doesn't overfit, because when you take transformation and use higher dimension variables, the model tend to overfit the data. So ensure that doesn't happen. So how do you do that? You just check for the test error. So check the mean square error in the test dataset, not the training dataset. Training dataset is the one you will be using for development of the model, where to evaluate model you should always use the test dataset, okay, or the validation datasets. So that's what you need to do. So that's the these are the 4 important questions I discussed. To get more videos, just subscribe to our channel and visit our website, which is in the description section of this video. Thank you.
The first question, which is on missing values. So one of the questions that is often asked is why keeping variables with high missing values is an issue in a predictive modeling. When you keep variables with high number of missing values in your model while building models, then there is going to be a number of problems. So one of the problem is that you will be losing information, and the results from your models is going to be biased. Okay, so one should ensure that variables with very high missing values, a very high number of missing values, should be kept away from the modeling, or should be dropped from modeling, right? So these problems, let's understand these problems, 2 problems. So here is an example. We have got data for customer income, customer age, and gender, right? So if I use all 3 variables in the model, where customer income is having quite a number of missing values, right? Out of like 8 observation, 5 of them are or 9 observation, 6 of them are missing, right? So if I'll use this data in modeling, so 6 observations which where customer income is missing will be removed from the entire data set, and only the model will run, or the statistical software will give you results on data for customer income not missing, right? Or in other words, the entire row corresponding to the missing value of customer income will be deleted, or will be dropped from the analysis. Now we'll be losing information if that happens. Now that can potentially give us biased results. Why? Because if there is a number of observations which are going to be removed from the data set before even the algorithm runs, then a certain segment of customers are not going to be represented in the final data set, right? Because say for example, in this case we have gender, male and female, right? So if you say that most of the observation in the missing case are male, right? See for example, out of the 6 cases, 4 of them are male, right? So you are removing 4 observations from your data set, and finally you are underrepresenting the male population in your analysis. So that's going to give you a very biased result, right? So that proportionate of gender, like male and female, has to be represented in the sample data that you are using for modeling. So missing value causes this problem. So one of the solution to this is that remove this particular variable. If it is important, then you can use variable missing value treatment later on, but if it's not so important variable, it's good to drop this variable. So that's one variable selection criteria, that with high missing values you can think of dropping the variable. The next question is, how does variance play a role in variable selection? Well, you always expect the independent variables to have very high variance. So why is that so? Well, if the independent variables got very high variance, then its ability to explain the variation in the dependent variable will be high, right? Or at least there is high chance, there is relatively higher chances that its ability to explain the variation in dependent variable will be more, right? So let's take an example. So we have got one dependent variable. The first one is dependent, and there we have got three independent variables. Independent variable 1 is all the values are constant. All the values in this independent variable are constant. That means if you compare the values from dependent variable with independent variable 1, it doesn't really change, right? Even if there is a change in the dependent variable, there is no change in independent variable. That means they're not related at all, right? Irrespective of irrespective of the values of independent variable 1, the dependent variable is changing without following any pattern. So this variable, independent variable 1, is not very useful. Now go to the independent variable 2. Now you see that there is some sort of variation. There are two values, 2, 1, 1, but the variability is much less, right? There are only two values, right? So you can see that last four observations, independent variable takes the value of 1, but dependent variable takes very different values, 48, 60, 70, 88. It's increasing, but independent variable 2 is actually constant. That means a major chunk of these observations are actually not very not very related, or there seems to be non-dependency. So although this is better than independent variable 1, you cannot use independent variable 1 here. You have to drop it. Independent variable 2 is better than independent variable 1 in terms of its ability to predict, but it's of course not the best one. Now let's go to the last variable, independent variable 3. Independent variable 3 is actually changing, right? Every level it is changing from 1 to 6. So now you try to compare it with the dependent variable. You see that with increase in independent variable 3, dependent variable is also increasing in that order. So we can see some sort of a pattern. So independent variable 3 is the best variable out of these three independent variables to predict the variation in dependent variable. So you can drop independent variable 1 and 2 from this analysis and only go with independent variable 3. The next question is, how does correlation play a role in variable selection? Well, ideally low correlation between independent variables is expected. So between independent variables you always expect that they are very low correlated, and you always expect high correlation between dependent and independent variables. Now you have to be very careful here. So what we are saying is that if there is high correlation between dependent variable and independent variable, then it's good. Why is it good? Because you always want independent variable to explain dependent variable, so they have to be very related, right? Much more relation between them, good for it. But between two independent variables, right, which are in the right side of the equation, there should be less correlation. And the explanation for this is that if they are very highly correlated, then there will be redundancy, right? You are using the same information again and again. So let's take an example, it will be more clear. Say for example, we have got two independent variables, net income and gross income, and the correlation between these two independent variables is 0.9, right? Now should we use both these variables? or should we just drop one of them? Well, you always see, intuitively, you just, if you even think, gross income and net income tend to be very similar variables, right? So they are highly correlated, right? Now these are two independent variables, so there is a huge overlap between gross income and the net income, right? So it's always good that we drop one of these variables from the variable from the model, because otherwise you are using the same information again and again and making the model more complex. There are also more technical issues related to this. We'll not go into the details of it, but yes, when there is high correlation, try to get rid of you know as many variables as possible. So what we are essentially trying to do here is that giving more information to the model with less number of variables, right? That should be the motive. The next example is it's a real correlation between dependent variable and independent variable. So profit is our dependent variable and age is our independent variable. Now the correlation is 0.05. That's a very low correlation. That means profit of a company is actually not related to the age of the customer, right? They're very less related, right? Or the correlation is very low. So it's very unlikely that age will explain the variability, or age will be able to help in predicting profit of the organization, right? So we may also think of dropping age from the model if it is not helping to predict. So these these are some of the simple way of selecting which are the best set of variables before you start estimating your final model. Or if so these are some of the very basic things you can use to drop some of the variable not so useful variables. The next question is, how does R square play a role in variable selection? You always add the independent variables which increase R square of regression, or in other words, any independent variable which increases the R square of regression model should be retained in the model. If a variable is not increasing, then and it's not very important, then you should think of dropping it. Not all the time, because maybe the variable is important for explaining the problem statement. Then you should keep it. Otherwise, if it's not that an important variable and it's neither increasing the R square value of the model, then better to drop the variable if you have too many variables. Otherwise, if there are only few set of variables, then you do not have much of luxury of dropping. You only have very small set of variables, then you can think of keeping all of this. So when there is a question of dropping one of the variables from two variables, say we have got variable 1 and variable 2, and so which one of these variables is to be retained and which one is to be dropped? So how do they take the decision? Just add variable 1 to the model and see how it is increasing the R square. Next, drop the variable 1. Now you add variable 2 to the model. Now see how the R square value is changing. If the R square value changing more in variable 1, then it should be kept or it should be retained. Variable 2 should be dropped, right? So the one which is increasing the R square value more should be retained. Now the next question is, how variable transformation play a role in variable selection? This is a little complicated, so let's try with an example. Let's say we are trying to model income with respect to age. So we want to know how age impact income, or how we can predict somebody's income with respect to age, right? So that kind of a model. Now we know that income increase rapidly with age initially, and then it gets settled down, and then actually drops after a while, right? Especially in blue collar jobs, right? So how do we model this, right? So if you have a linear relationship between income and age that we can see here on the left hand side of the graph, if y is in your income and x-axis its age, and you say that there's a linear relationship or there's a straight line relationship, that's wrong, because income doesn't increase linearly with age. In fact, it has a non-linear relationship, because income actually grows and it actually increases in a decreasing way, right? So instead of using age as the independent variable, we can actually use the logarithm of age. So we can drop age from the model, from the set of variables we have for model, and instead we can take transformation of that variable, logarithm transformation of that variable, and use that transform variable in the model. That will be more appropriate, and that will be more suitable for the forecasting and also for explaining things later on. So that's also one way of selecting the best set of variables for the model. The questions are like this. The first question is, what is the problem of heteroscedasticity? Well, the problem of heteroscedasticity refers to a situation when the residuals in a regression do not have uniform variance. So this is one of the assumption in the least square regression, that the errors should follow uniform or should have uniform variance. Well, this problem arises when there is variation in the observations across. There is an uneven variation. Okay, and I'll talk about what is an uneven variation across observations, and it is mostly seen in cross-section data, where you will find that the variation actually change with respect to the observations. So here is an example. You can see that the variation is lot less in the initial period, and later on you can see that the variation is lot more. So that's a typical case of heteroscedasticity. One of the example that we can take is if you plot weight versus height, right? Weight versus height. Now, say for example, if you increase the age of the child from 10 to 15, you can see that the height increases from say 20 to 25 kg. But if you increase the age of the age of child, or we keep on including more children in the age of 15 to 20, and you see the variation in the weight is between 30 to 70. Now you can see the there is a 5 years of difference between the ages, but if you take the weight of the children, the variation is lot more. In one case the variation is only 5, the other case it's 40. So that means there is uneven variation in the observations. So there are typical cases where the heteroscedasticity happen, and it's primarily a case of cross section data. So how do you and why do you really worry? Why do we ensure that it doesn't present in the data? It tends to give inefficient regression results. So you will get incorrect standard error. So incorrect standard error means your standard error is either underestimated or overestimated. Both are bad. You cannot interpret your results if you have incorrect standard errors. Another indication of heteroscedasticity is when you see the errors. Now the errors should be uniformly distributed across this the line, right? So it should pass through uniformly, and you will see that some cases you will see that there is a deviation. Some observations are lying far away from the other observations. So chances are there your heteroscedasticity is present when you have cases of outliers lying on the both sides of the this particular line. So one of the best way to detect heteroscedasticity is to do this plot, create this plot and see how the observations are distributed. So the next question is, how do you detect the problem of heteroscedasticity and how do you correct? As I've said, graphical plot is a good one, but there are also statistical tests which can be performed. White test is the one which is performed. The Bruce Pagan test is also performed. You can use proc model in SAS if you're using SAS to come up with these statistics. So how do we correct the heteroscedasticity? There are different ways, but one of the ways is to use the weighted least square instead of the ordinary least square. So the weighted least square ensure that it handles or it is able to handle the change in the variation or in your cross section data. So that's important thing. The next question is, what is the problem of autocorrelation in regression? So when error terms for one period is correlated with error terms in different period, we call this case as autocorrelation, and this is a problem. We expect that the errors terms should not be correlated, and this is a problem in time series data when we have taken data for 2 or more time periods. So if error t is correlated with error t minus 1, then we say that there is autocorrelation, or there should be some sort of correlation between the error terms. So what happens when there is autocorrelation and you go ahead with your simple regression? Well, your standard error tend to be underestimated, which will cause problems in the statistical test. Your statistical test will not be valid. So this is faced with data which is collected over time. So if you have taken data for cells data for different years, most likely your cells values will be correlated across time, right? Correlated over the time. So you face problem of autocorrelation there. So how do you detect presence of autocorrelation and how do you correct autocorrelation? Most of the times we will come across autocorrelation of first order. So first order correlation is something that is that can be detected using the statistical test known as Durbin-Watson test. So here is the Durbin-Watson test formula. You have error from two different series, EI and I minus 1. So you are trying to see the AR1 autocorrelation, that means it's a first order. So the rule of thumb is that if the DW statistics or the Durbin-Watson statistics is close to 2, then there is no autocorrelation, otherwise there is autocorrelations. What if the errors in regression don't follow normal distribution? So and what tests do we use to test for normality? Well, the test of hypothesis cannot be performed on the estimates if you face error terms, non-normal error terms. There is no issue with estimation. You can always estimate. You can come up with your OLS estimation, but we cannot perform test of hypothesis because test of hypothesis is totally related to the fact that the data is normally distributed, right? So that if there is no normal distribution, then you cannot come up with a 5% or 1% interval and test your parameters with your P and T value. So all these things are related to normal distribution, so you cannot really do all these things. So how do you detect, how do you find that it's not normal or it's normal? So the most popular one are the PP plot, the probability plot, or the quantile plot. Now here is an example of PP plot. Most software will give you this plot. So there is a theoretical distribution of normal distribution and then the actual distribution of your data. So ideally in a normal, if your data is normally distributed or your errors are normally distributed rather, then you will you will see that the points will be lying on this particular line, in the diagonal line. Only then it's normal. If there is points lying here and there, then there is slightly non-normality. Like in this case, you will see points are lying on the upper side of the line, so there is some kind of non-normality. There are also statistical tests available like Kolmogorov-Smear tests, Shapiro-Wilk test, and Anderson-Darling test, which can also be performed to find out if the errors are normally distributed or not. Most of the times you will see that if your variables, continuous variables, are normally distributed, then automatically the errors will also normally distributed. So that needs to be checked. Next question is, what are R square and adjusted R squares? Well, anyone familiar with regression would know this, but people often confuse with R square and how to and when to use R square. So R square tells us how well the model fits the data. So this is the first part of the answers, but technically it means something different. Technically it actually measures the percentage of variation explained by the model. So you have dependent and independent variable. So you are modeling for dependent variable, right, or the variable of interest or the target variable. So how much of variation which is measured in terms of variance is being explained by your model that you have estimated. So that's nothing but your R square. Always lies between 0 and 1. Sometimes it's negative. It cannot be negative though. So if it is negative, then there is something seriously wrong with the model. And the more it is close to 1, the better is the model. An adjusted R square is another version of R square which penalizes for adding extra independent variables. So we always want a parsimonious variable. So what do we mean by parsimonious? That means model with the least number of variables. So why we need least number of variables? Because if you can achieve high R square with less number of variables, then it is easy to implement, easy to interpret. So that's a good model. That is supposedly a good model. So if you keep on adding more independent variables to the model, the R square value should actually go up ideally, but adjusted R square will go down after a while because it penalizes for adding additional variables. Or
The often asked question in interviews is, what are the different types of commonly used model validation you know of? Well, there are several types of model validations people use in industry, but some of the commonly used model validation techniques are out of sample validation. So you take a different set of sample observation to test a model to see if the model is working fine, and that's known as the out of sample model validations. Like in this picture, you can see you are comparing the ROC value, the receiver operating characteristic value of several models, and the one which is performing best, you are choosing that model, or you are actually trying to see if the model is performing well in different types of samples. So out of sample validation is to take a sample that is different from the one you have used for building model, right? So that's known as out of sample validation. Out time validation is the one, like, if you have taken data for 2011 for developing your model, you can take data for 2012 to test your model if it is working fine. So the idea is that if the data is working fine for one time period, is it working fine for a different time period, right? That's known as out time validations. Then there is cross validation. So cross validation is taking multiple samples to test a model, right? So out time sample validation, you take a single data or single out sample data to test your model, wherein in the cross validation you actually take multiple subsamples or samples to test your model to see if the model statistics are consistent. So you check consistency of your model by looking at the cross validation. Then we also do the error evaluations, right? Once you have done the modeling, you test a model, test your the error from the model, right? For many, for a number of statistical models, the errors has to be completely random, as there should not be any pattern in the error. That you do by doing a lot of statistical tests and do plotting graphs for error. So that's one of the way to you do your model validations. That's important because error evaluation tells you whether the model is actually following all the theoretical assumptions in your required for your model acceptance, and that's important. And you also do sometimes KPI comparisons, right? And it depends on which industry you're working in. In banking and financial industry, they have got their own KPIs. In supply chain, it has got its own KPIs. In medical or clinical research, they have their own APIs. Similarly, on marketing, sales, they have their own KPIs. Sometimes the KPIs, the domain-specific KPIs, are compared across different models to see if the model KPIs are also performing well for different samples, for different time periods, and so on. So that's more like a business model validation, where the business themselves validate the model with their one set of expert expert domain knowledge. The last one is the stress testing. This is also often used in BFS, banking and financial service industry, wherein people use this technique to test models, whether the model work fine in extreme scenarios or in bad scenarios like recession or a stock market crash or a drastic change in the government and how it impacts banks and its profit and so on. So these are some of the commonly used techniques, but there are even more validation techniques available. You can take a look at it. So what are the consequences of not doing proper model validations? Well, there are several consequences. Of course, there are bad consequences only. You'll never have good consequences of not doing model validations. So one of the consequences could be the model may not perform well in the new data. The purpose of building the model is to use it for new data, but if it's not working fine there, then there's no reason for building a model. The model may not work fine for a longer time. That means it may work fine for few time periods from the time you implemented the model, but it may not work fine for a very long time, or for expected number of time periods that you wanted the model wanted to use that model. So you need to redevelop that model, and which will by doing so you need to incur you have to incur more cost, a higher cost. So that's not good. And the model may not perform as expected in extreme scenarios, right? So you should many a time this is a requirement, especially in industry where there is there is volatility, or there is changing scenarios, uncertainty. You should many a time the expectation is that the model also will be able to predict the extreme scenario or bad scenario. But if you haven't done the model validation properly, the model will not be able to perform well in such scenarios. So that needs to be taken care and needs to be incorporated in the modeling in the model itself while finalizing it. Sometimes the model could be erroneous, like in the previous slide, as I was talking about the error evaluation. If you're not evaluating a error properly and comparing across different set of samples, then the model could be totally erroneous, and specification of the model could also be wrong many times. So that's also one of the bad consequences. How is model validation different from model monitoring? Well, there are several ways it's different. There is some overlap also. They're similar terms. Many times the model validation team also does the model monitoring, but they are different in few ways. One is purpose. The purpose of model validation is to finalize a model. finalize a model, right? So this is during the time of developing a model, where you are developing a number of models. You are developing multiple number of models, and out of these multiple models, you are trying to finalize which one is the best model out of these models. So for that, you do model validation, whereas model monitoring is done only after the model has already been implemented. The model is already in production, and you are trying to monitor it on a regular basis to ensure that the model is performing well. So this is to see monitoring performance, right? The moment you see that the model is no more performing well, or it's not performing as expected, then you need to inform your modeling team, and the modeling team will re-estimate the model or redevelop the model. So that's the purpose. And then time. The time for model validation is mostly before the model is implemented in production, whereas model monitoring is only after the model has been implemented, is already implemented in the production, and people are using, or business is already using the model. So the time of doing this is also different. And the metrics, model validation metrics are mostly statistical, whereas model monitoring metrics are both statistical as well as there are some business specific model monitoring specific. That means if I'm building a profit model, okay, a model that predicts profit, or it finds out ways in which a business can make more profit. Now, if a model is doing well statistically, the parameters are all fine, but the profit of the company is not going up because of some reason. It may not be due to the problem in the model, but it may be because of some different scenario that has happened in related to that business. Maybe more competition, maybe change in the government, maybe some situation that has arisen. So the model has to be rebuilt again. So the matrix used for model monitoring is most of the times related to business, and is different from what you use for model validation. Another question that is often asked is, what is model re-estimation, right? So if you're using a model, it will not be used forever. It has to be updated. So why is a model need to be updated? Well, the data that you have used for modeling will be different after a while, right? Because of the changing nature of business, because of changing nature of customer behavior, because of introduction of new technology, right? Like if you build a model, let's say 10 years ago, there was no smartphones, or there were less number of smartphones. But if you look at today's consumer market, it's driven by more smartphone use, right? People buy and do all financial transaction using their smartphones, right? So the customer behavior that used to be 10 years ago will not be now. So models need to be re-estimated or redeveloped on a periodic basis. So model re-estimation and redevelopment are different, right? Model re-estimation is using the same data, same number of variable, only you are estimating it again, right? You are estimating it with maximum likelihood or any other estimation technique. You are simply running your proc regression again, but you are using this proc regression in SAS or your R code for regression, but you're using the same input data. Input data is different, but the same number of variables, same number of input variables, or the same variables, right? So the model specification is same. Model specification is same. Model specification is same. Only there is a change in the data, and you are estimating it again. Whereas model redevelopment means there will be changes in the data, as well as there will be changes in the variables, input variables, and there will be more number of transformation. There will be some variables which will go out of the model, some new variables which will come in. So that's model redevelopment. And how are the different, when do you want to do it? Well, model re-estimation is actually done almost every year or every quarter, every 6 months, whereas model redevelopment, which is a more complicated task to do, is actually done every 2 to 3 years time, and it actually depends on the industry we're talking about. So model estimation is simply a part of model redevelopment, which is a much bigger task. Another question which is often asked is, what is sensitive analysis, which is in context of model validations. Sensitive analysis is a very popular thing in financial service industry, where and also in the medical science industry, clinical research industry, where you try to measure the uncertainty or the impact of uncertainty in certain independent variables on the dependent variable. So if a model is like this, so here is a model, right? Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and beta this. There are three independent variables, x1, x2 and x3. Now, how do you know that which one of these variable is very important for your model, and if there is a change, slight change in such variable, there will be great impact in your dependent variable, right? So some of the variable will be very important. Let's say x1 is very important in your regression, right? Not all variables will be of equal importance to the model, and any slight change in the model x, in the variable x, is actually having, or actually putting a lot of changes or a lot of variation in the value of y based on x, and the variable x, let's say, is very uncertain, right? Then it's a very difficult model to have or to use. So x1 is very sensitive. So quantifying that sensitivity because of the uncertainty of certain independent variable is known as sensitive analysis. And why do you do that? To check the robustness, because you should ensure that the model is working fine in every scenario, in every uncertain scenario. Now, if for one particular independent variable the model is not working fine in an uncertain scenario, you have to be extra careful for that, right? And then you quantify your uncertainty because of by doing so. And you also in this process you also identify what are the sensitive variables. Let's say there are 8 independent variables. Out of these, 3 are very sensitive, so you need to take extra measure to ensure that the sensitive independent variables do not make adverse impact on your model in extreme scenario. And you also simplify your model. Sometimes you need to drop the sensitive, extra sensitive variable, independent variable, even though they are doing they're contributing to the model, because they are so uncertain, they are so volatile, you cannot use them in the model. So one of the way to detect is find out the sensitive variables are one at a time test, or OAT test. So what you do is that, say for example, this is one the model, we have 3 independent variables. So you simply drop one of the variable, drop x1 and do the regression, and then drop only x2 and then see how the regression is and how the performance is. So what you do is that what you're essentially trying to do is that so because of the absence of one variable, let's say x1, how is the model getting impacted? Similarly, so you take only one variable at a time and drop it, and put all variable, keep all rest of the variables, and see how the model is performing and so on. So the impact of one variable will be known only if you drop it, or you simply include that variable and drop all other variables. So dropping one at a time is one of the technique, although it has got its own demerits, because you do not you do not know the simultaneous effect. So sometimes a number of variables together make impacts. For example, it could be that x1 is independently doing fine, but along with x2 it is doing a bad impact, or it's very doing sensitive impact. So simultaneous impact is also an important thing that need to be captured before finalizing the model. So these are some of the important questions asked in interviews. You can click on the link below to watch all our videos, and do subscribe, do comment. One of the commonly asked question is, what are the the common data quality issues faced in modeling? When you build models, you face a number of data quality issues, and before you start building model, you need to handle these issues or overcome this issue, because otherwise you will not have a good model. The issues you could face are, there could be issues with data type. Okay, like values in column should be of same data type, right? If you have a column, let's say salary, right? Salary, it has to be a number, it cannot have a text value, right? Similar issues can also be found in other columns. So ensure that the data quality, the data type of a particular column has to be same throughout, otherwise it's a data quality issue, and you need to correct that first. Range constraints, like some data always fall in a particular range. For instance, probability. Now probability always has a minimum value of 0 and maximum value of 1. It cannot be a negative number, and it cannot go beyond 1. It has to be between 0 and 1. So that's a range constraint. That is always there for a number of different variables, and ensure that you check that before you go ahead with modeling. Mandatory constraint, in certain data, in certain variables, they cannot have zeros or empty values. So ensure that it doesn't have a particular value. It could be 0, it could be a certain number, or it could be the case that the value, the column cannot be empty. Okay, so that is another important check. Unique constraint, a field must be unique across data sets. Like if you're having several data sets across different projects, your variable should have unique definitions or unique values across all the data set. It cannot have multiple values, otherwise that's a erroneous data, and ensure that it gets captured before you build models. Value constraint, so for instance, gender can only have male and female. It cannot have 4 or 5 values, right? So that's one important check ensure to do. Constraint on pattern. Okay, for instance, if you are having a data on phone numbers, then sometimes it has to be it has to be with the ISD code, and the ISD code is between bracket. Ensure that it's proper for all the data points. Spelling error, sometimes your data could have a spelling error, that could cause issues. Missing values and the reason behind it. This is very important data quality issues to be checked, and ensure that you find a reason behind why is the data missing in a particular column. Outlier detection. Outliers are a big problem in modeling. Ensure that you detect outliers and remediate before you start building models. Cross-field validation. For instance, the date of somebody is joining the firm cannot be before the date of his birth, right? The simple thing. Or date of a patient discharge from hospital cannot be before date of his admission to the hospital. So these are very small checks, but sometimes because of erroneous data because of data received from wrong resources, you might find such issues, and ensure that all these issues have been taken care of before you start building models. Another important question often asked is, what is the life cycle of a data science or analytics projects? So simple questions, but even sometimes experienced data science people make mistakes while answering questions. The reason is because the steps involved in data science or analytics projects differs across domains, and it also differs depending on which companies you're working for. But there are some important steps that are common between data science projects across domains. First one is data acquisitions. So the first thing is to get data from internal and external sources and collate them, and ensure that you have a proper data in place before. So that's the second step. And we also looked at what are the data cleaning steps or data quality issues that you might face. So all that has to be done in the step. Modeling, then you go ahead with building models using statistical algorithm or machine learning algorithm, and you validate your model and select the best model. Then you evaluate and interpret the models. Models are evaluated and tweaked so as to improve performance. And then you deploy models to ensure that your model is in production and working fine. And once the model is there in production, you monitor on a regular basis to ensure that model is performing well. Just in case you find that model is not working fine during the monitoring process, then you flag that, and then you rebuild the model or re-estimate the model. So these are the common steps. Again, it all depends on which project you are working in, and there could be several changes to these steps. How do you control bias in a model? Well, you can control bias in the model by doing the following things. Ensure that the sample that you are using to build model is representative. And what do we mean by representative? That means the distribution of different variables should be same across samples, okay, or population and sample. You have a large population and you take a sample from that. This is population and this is sample, okay, and you have, let's say, two variables, v1 and v2, and you have taken sample as v1 dash and v2 dash. So if the mean, the standard deviation, okay, and then maybe the distribution, the sample distribution, so all that has to be similar also in this sample, and that only then it is a representative, otherwise it is not. So the sample statistics should more or less match, if not exactly same, at least to be very close to each other. So that's representative. There are also other statistical tests to prove that your sample is representative, but even without statistical tests, you can test whether your sample is representative or not. Ensure that you have a large sample to build model. That always helps. Include all important predictors. Otherwise, you will be not having a very good model. Ensure that as many predictors are tried out, at least. Not all predictors are going to be in the final model, but ensure that all the predictors have been tried in the model. Avoid using highly correlated variable. Otherwise, that could create issues, or that could bring down the performance of the model on several occasions, and also create issues while interpreting the models. So that's should be kept in mind. Randomize the sample selection. When you take a sample, ensure that it's a random sample. There should not be any bias in that. So the sample selection should be simple random or stratified random sampling, and such method has to be used. Explain what is the lift of a model. So lift is an indicator to measure how effective the model, and often in marketing analytics, in credit risk analytics, lift is a very commonly used matrix used to evaluate model performance in the productions. And lift is given by target response divided by the average response. So for instance, let's say that the model has been built for a click-through rate of ads. So the CTR is 5% without the model, and CTR is 15% after the model has been in use. Then the lift would be just 15 by 5, which is 3. Although it's simple to calculate, but normally in productions or when we find it out in real uses, we do it for different quantiles and use that as a measure for a marketing strategy or risk strategy. So how do we do that? Let's say, for instance, we calculate this lift using the same formula for, let's say, 10 quartiles. Okay. So that would be, for every percentile, for every decile we would have a lift, right? So decile 1 to up to 10, and we'll have a lift, corresponding lift, right? So if you have that in place, we can say that a certain percent of click-through rate can be achieved by just looking at the first two quartiles, first two deciles. And that would be very useful because given the cost involved in marketing programs or handling risk, it is always good to look at only the top quartiles. And what is the click-through rate in the top deciles is very important from a strategy point of view. So for instance, we can say that 60% of this CTR or click-through rate is happening in just the 20% of the ads or the top two deciles which have been scored by the models. So that's exactly is lift used for. Explain identification handling of outliers. Well, how do you identify outliers? Firstly, through visualization, you plot the data and you will find many data points, very different from the other data points. Only a section of data points are, at a very distance from the usual data points or most other data points. There could be outliers. Other methods could be use the 3 sigma rule. Like anything that lies beyond 3 standard deviation from the mean can be treated as a outlier. Although this is not a rule of thumb, many other consideration has to be made, whether that actually affects your model greatly or not. Is that an important variable? Is that an measurement issue or is a proper data? So all that has to be taken into consideration. And in case you have only small number of data points lying in that area, then that there is hardly an issue in that. Other methods could be using box plot, QQ plots, and then there are statistical measures like measuring the Cook's distance and taking a threshold, and anything that is beyond the threshold, just remove them. So that's one way of identifying outliers. How to handle them? So you can remove them from the data if there is hardly any effect on the model. Sometimes if you transform the variable, you take logarithmic transformation or any other type of transformation, then also outliers effect are reduced, and then you have a better data in place. In case you cannot remove them, then you can use robust statistical estimation methods. Like robust regression is one method which helps getting rid of outliers. Alright, you can also use weight of evidence, often used in credit risk industry, which helps you to get rid of outliers. So weight of evidence transformation of variables completely helps in getting rid of outliers. Explain what is curse of dimensionality in modeling point of view. So this is often cited when data is of high dimension. That means there are a lot of variables, and that actually creates problem. Although it helps in some sense, but it also creates issues. It reduces the number of options that you have in terms of choosing algorithms. Not all algorithms can be very effective in high dimension. In fact, some of the algorithm cannot be estimated. So if you're using ordinary least square algorithm, your number of independent variable has to be less than the total number of data points. Okay, otherwise OLS cannot be estimated. In fact, many other algorithms cannot be estimated through this. So data availability is an issue in such a case, because if you do not have enough data, many algorithm will not just work. So that's the issue with high dimension thing. And then significance test is an issue. Although for prediction purpose, you can build some of the algorithms, but the actual use of model is not just for prediction, it's also to know the inference or the relations between variables, and for that you need significance test, statistical significance tests, and that won't very feasible in many cases, and many algorithms are not suitable, and some algorithms are highly suitable for such cases. So that's pretty much what's known as curse of dimensionality. How to test regression classification, whether they are working fine or not. For regressions, the standard measures or matrix when we look at are the follows: R square, it explains how much variation the dependent variable is explained by the set of independent variables. Root mean square error, and we also look at the Akaike information criteria and squares Bayesian criteria. So these are commonly used statistics used to select the best model out of several regression models. For classification, we used C statistic, accuracy, misclassification error, again AIC and BIC as well. Explain the uses of resampling methods. So what are the uses of resampling methods? And you might have come across many algorithms which uses resampling. So resampling is about repeatedly drawing samples from training set and refitting the model of interest on each sample in order to obtain the additional information about the fitted model. Now you have a model in place, and then you fit that model with several data sets drawn from this training data set, and then you see how your model is varying, and you get a lot of insight about your model when you take different subsamples from your training sample. And sometimes it also helps you bettering your model or improving your model. So some of the common uses are cross validation to ensure that the model is working fine, not just in training set, also in new data or test set. So cross validation is one area where you take the number of cross validation, like k-fold cross validations, often use resampling techniques where k number of samples have been taken from your training set to evaluate the model, and then you average it out, right? Anyone familiar with cross validation knows that resampling is very much used. Bootstrapping is used when you take a sample but with replacement, right? And bootstrapping is used in ensemble modeling, right? In bagging, boosting, and random forest, and many other variations of bagging, boosting, right? Like gradient boosting or XG boosting, extension boosting. Many such boosting algorithm uses bootstrapping. So thank you so much, and please subscribe to our channel.
One of the most often asked question on factor analysis is how is factor analysis used in data analysis? Well, factor analysis as such is not a statistical technique. So how is it used? How it helps in building statistical models? Well, if not directly, indirectly it helps a lot. So one of the most important use of factor analysis is doing variable reduction. So you can, if you have a large data set, large number of variables are there, then you can reduce to a lesser number of variables by using factor analysis. The second use is when you have highly correlated data, like the attributes or the
the variables you have are highly correlated. So when you have highly correlated variables, you cannot use or you cannot build a good model. So to get rid of the highly correlated variable and to get down to a smaller number of uncorrelated variables, you can use factor analysis. And the last use, which is more technical in nature and less understood, is finding out the latent factors. Factor analysis helps you in finding out what are the unobserved or what are the hidden factors behind certain events or certain occurrences. Okay, for example, say for example there is customer satisfaction. Okay, satisfaction. Now customer satisfaction is something that cannot be seen, but it is hidden in some factors, right? So factor analysis will be able to find out the hidden factors by grouping number of variables. So what it does is it groups in certain way, it groups variables or attributes and gives the hidden factor. So somebody who is familiar with factor analysis will understand the last point, but nevertheless the first 2 points can be the first two uses of factor analysis is very important and can be performed by anyone who is only who has only basic knowledge of factor analysis. The next question often asked is, what are the differences between the exploratory factor analysis and the confirmatory factor analysis? Somebody familiar with factor analysis must know that there are two types of factor analysis broadly. One is exploratory factor analysis and the other one is the confirmatory factor analysis. The difference is in the application of these two techniques. Well, the exploratory factor analysis is used to explore the underlying factors, whereas the confirmatory factor analysis is used to confirm the underlying factors, and we have talked about the factors in the previous questions. Let me give an example. It will be clearer. Okay, so I've got we're doing customer satisfaction. So this we have a survey data. We have customer satisfaction. Okay, so it's a survey data. So from say from 1 to 5, some people have got ratings on customer satisfaction. Now customer satisfaction depends on the suppose the color of the product, then the number of days the customer has used this product, number of days, and then the service help provided by the company, and the replacement cost. Okay, and it could be, we can have more number of variables as well. Okay, now we have got 4 variables. Customer satisfaction depends on the product features like color and number of times it has gone for repairing, and then services and how much cost the customer had to incur for replacement, and so on. Now through exploratory factor analysis, one can explore the relation between these variables, okay, and come up with some latent variables. Okay, now you can see the first 2 variables are the feature of the product. Okay, so we can say that this 2 variables represent one factor known as satisfaction with product, and the next 2 variables are somewhat related to satisfaction with service. Okay, so the overall customer satisfaction depend on 2 main factors: satisfaction with product and satisfaction with service. Okay, satisfaction with service and satisfaction with products. Now these are the 2 underlying factors. So mathematically we can represent that customer satisfaction is equal to some form of uh, uh, product satisfaction plus service satisfaction with product plus satisfaction with service. Okay, so that's the equation. Now whether this equation is correct, so this is what you have, this is just an hypothesis. Okay, this is just an hypothesis. To confirm this hypothesis, to confirm that this representation is correct, you need to do the confirmatory factor analysis. So always you start with the exploratory factor analysis, come up with this representation of the model, and then confirm the representation that you have got from the exploratory factor analysis by using the confirmatory factor analysis. So that's the basic difference. Next question that is often asked is what are the differences between the factor analysis and the principal component analysis. This is a controversial one because PCA and factor analysis have come from different academic subjects, so there is a conflict, but the basic differences are, well, there is a similarity also. The uses of PCA and exploratory factor analysis in particular, they're pretty much the same. PCA is used for variable reduction. Exploratory factor analysis is also used for variable reduction. So the uses are pretty much the same, but the difference is mostly on computation. The way the principal component or the principal components are computed, and the factors are computed in factor analysis. So that's the basic difference between the factor analysis and the principal component analysis. So one of the mathematical difference I'll provide here, and it's very important and often asked in technical round interviews. So in the factor analysis, every variable, say variable 1, is a linear combination of beta 1 plus factor 1 plus beta 2 factor 2. Whereas if it's a principal component, it is a combination of linear combination of variable 1, variable 2, and so on. It could be more number of variables as well. So here is the difference. In factor analysis, each variable is a linear combination of hidden factors like factor 1 and factor 2, which are unknown, and you determine that. Whereas principal component, in the case of principal component itself is a combination of linear combination of variables. So it is the reverse, or it is the opposite of the way the factors are calculated in factor analysis. So that's the main difference between PCA computation and the factor analysis, computation of factors. What are rotations in the context of factor analysis? This is also an important question. Many times you will want the factors to be completely uncorrelated. Okay, that means say there are two factors in a data analysis, factor 1 and factor 2. The correlation between f1 and f2 should be 0. And when does that happen? The two variables or two series are have 0 correlation when they are perpendicular to each other. Okay, so this is factor 1 and this is factor 2, right? So this is perpendicular. That means they are orthogonal in nature. In that case, the correlation between factor 1 and factor 2 is 0. Many times this is a requirement, right? Well, these factors will be used as independent variables in the models, and you know that if the independent variables are totally uncorrelated, it's good for the model, right? Hence, in that case, you will be using the orthogonal rotation of the factors. So that's one of the rotation. many a times you want some kind of a correlation, that you expect that there is some kind of correlation between the factors. In that case, you will not be using orthogonal mm, rotation. There are other kind of rotations available in which you can actually keep some sort of correlation between the factors. The last question I'll be discussing is what are the uses of factor analysis? Like, where can you use, like, factor analysis is not a is not just a variable reduction technique. It is used as some sort of a modeling technique in a number of scenarios. And one of the most important scenario where factor analysis is used in the business, I'm not talking about the academics, it's in business, is in marketing. So in the case of survey data, if you have survey data, you are doing survey analytics, factor analysis is heavily used. So it's used for, like for example, it's used for knowing factors affecting consumer satisfaction. In academics and in other spheres, it's highly used in psychometry, where the researcher try to find out the factor responsible for performance of students. Performance of students in class. What are the performance factors, like economic factors, then education of parents, and social factors, and so on. So these are cases. So whenever you have you expect some hidden factors to be responsible for occurrence of something, then factor analysis, both the exploratory and confirmatory factor analysis, will be handy techniques to be used.
The first question that is often asked is what is forward selection of variables? Now this is a very popular way of selecting variables in regression models. So what is it? So let's say there are p number of variables we have got p independent variables, right? So in forward selection of variables, what is usually done is we first regress the dependent variable with each of these p independent variables. So when there is only one independent variable involved in a regression, we call it as a simple linear regression, right? So we perform p number of simple linear regression in the first step, and then we compute the residual sum of square, or known as the RSS, for each of this model, right? Each of this simple linear regression model, right? So we always expect that the residual sum of the square should be minimum, right? So if for a variable it is minimum, then it's the best variable, right? That means it actually is very close to, or it actually explains the variation in the dependent variable, right? So we arrange the p independent variable with respect to the residual sum of square, right? So the one which has the least residual sum of the square is picked off first, and then used in the model. We run the regression again, and then we select the next variable in the list. That means based on your residual sum of square. So the one which is having next to the list sum of square, so we take that, and so on, right? We first arrange it in the ascending order, and then select one by one, right? And we also see the significance level, right? So we keep on adding variable to the model with the lowest residual sum of the square, and the next lowest residual sum of the square, and the next, and so on, right? And then we set up the minimum significance criteria, right? So for a variable to be part of the model, we ensure that it should have a minimum significance criteria. That means the p value has to be somewhat okay. So usually it is 0.05, but you can actually change
you have perfect control over the p-value. You can set up your own p-value, but by default in most software it's 0.05, right? So that's why you start with a null model, right, without any independent variable, and then take the first variable with the least RSS, and take the next variable. Once the variable is included in the model, it will never be dropped from the model. So that's a criteria for forward selection, right? So, and the moment the minimum significance criteria is not met, we do not go further and we stop there, right? So that's the way we perform the forward selection of variables. So we reject a number of variables in this process which do not really meet the significance criteria. That means the p-value is greater than 0.05 or any cutoff value that we have set for this purpose. The next one is what is backward selection. Well, backward selection is actually opposite of forward selection, right? In the forward selection, we started with a null model, and slowly, or step by step, we added one variable, more significant variables, and went to the least significant variables and stopped at a point at the cutoff point, right? We do the exact opposite. We start with all p number of variables, right? And then we do the regression, and you will see that a number of variables out of these p variables are very less significant, right? So we again set out a cutoff score. Let's say the p value is again 0.05 is the cutoff. So when you take all independent variables and then do the regression, you will see a number of these p values, a number of these independent variables has an estimate with p value greater than 0.05. So you just drop, in the next step, you just drop the one which is the least significant and run the regression again. And then again drop the variable with least, which is least significant. And then again run this regression. You keep on doing that till the point where all your variables are meeting the cutoff criteria or the selection criteria, right? So we simply do the exact opposite thing. We keep on dropping variable instead of including variables or adding variables in unlike forward selection, right? The next question is, what is stepwise selection? Stepwise selection is also known as mixed selection. It combines both forward and backward selection. So it uses the benefit of forward selection and backward selection and combines and do a better job most of the times. So what it does is that a variable which is included in forward selection can also be dropped at the later stage, right? So the good thing about forward selection is that you actually include the good variables or the most likely to be significant variables. But the bad thing about the forward selection is that once a variable is included, you can never drop it again. The good thing about backward selection is that you can actually drop variables at any point of time in the selection process, right? But the bad thing about backward selection is that you start with too many unwanted or unnecessary or not so important variables, right? So how do we combine? We start with the forward selection criteria in stepwise and take only the most significant variables by the cutoff criteria, the p values, right? And go on adding one after the other, and see the significant value. But every time we find a variable to be not significant later point of time, even after getting added to the model, we can also drop it from the regression. So the steps are like that. Say for example, we have got 3 variables, and then let's say x1 is the most likely to be significant. That means when we first do the simple linear regression, that means y with respect to x1, we found that x1 is having the least RSS, right? So that's included first. And then in the next step, we have got x2, which is the next variable to be included based on the RSS. And now we have got x1 and x2 in the model. Now again we check the significance value. Now let's say the p-value of x1, which was earlier good in the first step, now in the presence of x2 has gone off, right? In forward selection we cannot drop it, we have to keep it. But in stepwise we can actually drop this variable. So we can drop x1 from the model and we only have x2. Now in the third step, let's include x3, which is the next candidate. Now we again do the regression with taking x2 and x3 and see if both are significant. If both are significant, we'll keep them. If one of them is not significant, we'll again drop. So the point here is that the moment there are a number of independent variables, a variable may be very good as an independent variable. That means when it's alone, that means it's alone in the model. But when it is there in presence of a number of other variables, it may not be a significant variable, or it may not be a very important variable. So we also try to find out the fact that a variable is not only very important when it is alone in the model, it should also be very important when it is combined with a number of other variables. So this is very important step in multiple regression, where we use a number of variables for doing the predictive models. Next question is, what are the main model statistics that is usually checked before we say that the variable selection is something that is getting affected because of the statistics. So the main model statistics which are usually used for variable selection are the adjusted R-square first. So the variable which increases the adjusted R-square should be retained in the model, or should be part of the model, or should be considered as an important variable. There are two other statistics which are also important. The one is archaic information criterion and the Bayesian information criterion, or popularly known as AIC and BIC. So we always expect that AIC and BIC should be list. So if we add a variable and which decreases AIC and BIC, normally it doesn't happen. I mean, you keep on adding variable, AIC and BIC are likely to go up. But you can actually keep on taking different set of variable and see where exactly AIC and BIC are list, and that set of variables are actually preferred, right? So these model statistics also help us in finding out the best set of variables for a particular model. Thank you. The first question goes like this. In an exam, there are 3 questions to be answered. Probability that you answer the first question correctly is 0.4. The second question correctly is 0.3, and both questions correctly is 0.2. The two questions, sub questions to these questions. What is the probability that you answer either first question, second question, or both questions correctly? Okay. And the second question, sub question to this question is, what is the probability that you get both questions wrong? Okay. So how do we solve this? So probability that you get the first question correctly is 0.4. Probability that you get second question correctly is 0.3. And probability that you get both questions correctly, 1 and 2, is 0.2. Okay. So let's use the Venn diagram. So this is first question, this is the second question, and this is the common area between them. That means getting both the answers correctly. Alright. So we want to find out what is the probability that somebody will answer either the first question or the second question or both questions. Okay. So we want to find out the union of this two circles, right? So how do we get? So probability of 1 union 2 is nothing but probability of 1 plus probability of 2 minus probability of 1 intersection 2. So that we know from the basic probability theory. Now what is probability of 1, which is 0.4, probability of 2 is 0.3, and probability of 1 intersection 2, that means the common area, that means somebody is able to solve both the questions, is 0.2, which is 0.7 minus 0.2 equal to 0.5. So the probability that one would answer either question 1, question 2 or both the questions is 0.5. Now the second part to this question is what is the probability that somebody will get the answer wrong? Okay, that means neither of these will happen. Neither the student will be able to answer question 1, question 2 or both the questions, right? So how do we answer this? Okay, well, the probability that somebody is going to get the question wrong would be given by 1 minus probability that one would answer out of these three options, right? So that means probability of 1 minus 1 union 2, which is 1 minus 0.5, which is 0.5. So probability that one would get the answers wrong is 0.5. Then the second question number 2. A student has the option of choosing subjects from out of these three subjects, physics, maths and computer science. The probability that somebody is going for physics is 0.5, probability that somebody is going for maths is 0.6, and probability that somebody is going for computer science is 0.3. And probability that somebody is going for both physics and maths is 0.3, and then math and computer science is 0.2, physics and computer science is 0.4. We have been asked to find out what is the probability that a student studies all three subjects. So if we plot a Venn diagram, we are going to have three circles, because we have got three options, right? Physics, maths and computer science. Physics, maths and computer science. Alright, so we have been asked what is the probability that a student studies all three subjects. Okay, so we need to find out this area, right? Area of this circle, because this is common to physics, maths and computer science. If we use the fundamental theory of probability, we know that P of A union B union C is nothing but P of A plus P of B plus P of C minus P of A intersection B minus P A intersection C minus P of A B intersection C plus probability of A intersection B intersection C. And we have been given these values, right? P of A, P of B, P of C, which is 0.6, 0.3 and 0.3 respectively. We also have the probability of A intersection B, that means physics and maths, which is 0.3, and then A intersection C is maths and computer science 0.2, and B intersection C, which is 0.4. Now we need to find out P of A intersection B intersection C, that means probability of mathematics intersection physics intersection computer science, this common area. Okay, so we know all these values. We also know the right hand side, right? P of A intersection A union B union C, right? So A union B union C would be 1. Why? Because the student has three options and he can choose just either one of them, two of them, or all three of them. So when we combine all three, we get a probability of 1, right? There's nothing apart from this. So the full probability is 1 in the left hand side. Now when we use this, we can get the answer correctly. So 1 equal to P of is 0.5 plus 0.6 plus 0.3 minus 0.2 minus minus 0.3 minus 0.2 minus 0.4, and then P of A intersects, P intersection maths intersection CS. So if you add this up, this is this is 1.4 minus 1 plus P of, we'll just denote it as P. This is what we want. Okay, so this is 1 equal to 0.4 plus P. So if we solve this equation, we get P equal to 1 minus 0.4, which is 0.6. So the probability that somebody will choose all three subjects, physics, maths, and computer science, is 0.6. So that's how we solve using the Venn diagram. Thank you. Which is a simple one, which is asked to the beginners, is name a few commonly used as procedures for data handling. Well, to handle data, you could very well use a data step, right? If you're familiar with SAS programming, data step is very useful while handling data in SAS, and it's very efficient. But there are also SAS procedures which are very useful and very handy when dealing with data. If you want to sort the data using data step, it's going to take a lot of lot of effort. But you have the SAS proc called proc sort. You can use that for sorting your data. You can merge your data using proc merge. You can append using proc append. You can copy one data set from one folder to the other using proc copy. You can export data to external file. It could be a spreadsheet file, Excel file, or a access file using proc export. You can use proc SQL to do a lot of things with your data. Like you can do inner join, you can do outer join, you can do all kinds of data cleansing and data merging, sorting, everything you can do using proc SQL. So you can essentially you can write your SQL query in SAS using proc SQL. So that's useful proc for data handling and data cleaning. Proc transpose, to transpose your data. Proc format, in order to format your data in certain way. You can format your column name, and that kind of thing you can do using proc format. Proc summary is something that you can use in order to summarize your data, which is also useful sometimes. Proc standardize, if you want to standardize your data, sometimes standardized data is used for data analysis. You may need this proc as well. So these are some of the important SAS procs which are very useful while handling your data. So what are the few commonly used SAS procs for data exploration? In the last one we saw data handling data, but what are the SAS procs which are very useful for data exploration? Proc means, you might have heard about proc means, proc core. Proc means you can use it for summarizing your data in order to get the mean, standard deviation, minimum, maximum, and then you can get so many other things as well. You can get a variance, you can get standard deviation, you can get the number of missing values using n-miss statement, and so on. PROCOR, you can get a correlation matrix which shows the correlation of variables in your data using PROCOR. You can use PROCFreq, to tabulate your data if you have categorical data. So you can use different categories against you can have your count of different categories of your data using PROCFreq. And then you have proc univariate if you want some kind of an analysis, some exploratory data analysis on a single variable. You can use proc univariate, wherein you will get mean, variance, covariance, and then you will get so many important plots like your normal distribution plot, histogram, and so on. Proc distance is an important one, where you can find the distance or close relationship between different data points. Proc ADE, if you want to plot a kernel density for your data, you can use proc ADE. Proc tabulate, especially for creating reports. This is very useful. So these are some of the important SAS procs you can use for data explorations. Next question could be, what are the SAS procs you use for data visualization? Well, visualization essentially in SAS is like creating plots. So you can use proc plot. Box plot can also be used if you are particular about creating a box plot. Proc chat, gchat, and then KDE is also useful because you will get a kernel density plot. In this case, SG plot is there, G plot is there, time plot, especially for time series data. If you want to fit a spline, which is similar to the kernel density, you can use TS spline. So to get into the details of these plots, you can always look at the SAS user guide, wherein the details have been given. So based on the type of plot that you are expecting, you can use either of them. What are the commonly data analysis procs that one would use while doing data analysis on SAS? The list is exhaustive, but I'm just providing very important ones, and especially from a beginner point of view. We use ANOVA for analysis of variance, ARIMA for time series forecasting, CALIS for structural equation modeling, cluster for cluster analysis, GLM for generalized linear modeling. Generalized linear modeling includes your linear regression, logistic regression, and that kind of stuff. MCMC, Monte Carlo methods, which is Markov chain Monte Carlo. So you can use MCMC for that. NLMix for optimization purpose. MCMC can be used for Bayesian also, Bayesian regression. And then PRINCOM for principal component analysis. PROCREG for regression analysis, whether it's linear regression or polynomial regression and so on. Factor for factor analysis. And Logistic, the very famous Logistic regression. Okay, so these are some of the important data analysis procs. For someone in the beginner of someone who is a beginner in data analysis, one should be familiar with all these SAS procs to be able to answer some of the data analysis questions asked in interviews. Okay, so one common question which is being asked in most interviews is, how do you perform your join using how do you merge data in SAS? Well, you can merge data in varieties of ways. One way to do is using the merge statement in base SAS. Okay, so for instance, you have been given an example, is this table A and this is table B. Now in table A we have got IDs, which is an unique ID, so 1, 2, 5, 7 is there. In table B we have also got ID, which is unique, 1, 5, 6, 8. So somebody says, or the interviewer asks you, that I want data only for the matching IDs. So how many matching IDs are there between A and B? We have got ID equal to 1. So here is also there. And then we have, okay, we have just one matching. Oh no, 5 is also there. Okay, so I've got 2 matching IDs. Okay, so how do you write a merge statement in order to be able to get the matching ID and the corresponding data for A and B? Okay, so this should be C and D. I'm sorry, this is C and D. Okay, so we want data for matching IDs. Okay, so what we'll do is we'll have to write an inner join statement using merge, or else you can use proc_SQL to use a inner join query. So that also we can do. So one would expect you to write a query and give it to him, simple one which can be written easily. Sometimes you would be asked that, okay, we want only the non-matching columns. Okay, so you will have to do a negation of negation of the inner join, or you have to perform an outer join. Sometimes you will be asked that, okay, we want all the columns from the left hand table and only the matching from the right hand one. So you might have to do a left left outer join. Okay, and sometimes the other way around, you want all the columns for right one and the the matching ones from the left one, or the first table. So you might have to do, in that case you have to do like the right outer join. These are some of the exercises you will be asked to do in interviews. Other questions that is often asked is, what's the difference between merging and not set statement. Okay, this is a confusing this is just to make you confused. If you are familiar with merge statement, you will never be confused with set. But people who are more familiar with proc_SQL, like I prefer proc_SQL over merge statement. Sometimes you get confused with merge and set statement. When you do a set statement, the data A just get appended below, just a set data B gets appended below A. Very unlikely you will have even you will never have a data right next to A using set statement. But if you merge them, the data B will appear here. Okay, so that's the difference. Okay, these are some of the important questions asked in SAS interviews.